it's only been maybe a minute and a half and the voltage is already recovered to 11.8 volts. That'll go up to almost 12 volts by the time I wait half an hour or so. And then once again you can look at a state of charge table and see that we still have around 30% capacity left in this battery. And that would bring us up to 100 amp hours if I could use everything that's left. So we tried 1500 watts, maybe 1300 watts. We've tried 800 watts, we got some more out of it, and now let's try about 300 watts more. See if we can actually get the full 100 amp hours out of this battery just by lowering the load. Now, to do the load here, I have my super high-tech load bank. And you can't buy this in stores because it's patented technology. So if you build one of these, you're going to have to pay me some royalties. Of course, you won't be able to figure out how to make this yourself because it's way too complicated. But anyway, I have it plugged in. Turn the inverter on. And I'm going to turn on 3 100 watt light bulbs. 1, 2, 3. So we have 300 watts of light bulbs going. And you can see that it is drawing about 28 amps from our battery. And the battery voltage is still at 11.5 volts. I'll now take my stopwatch, reset it, start it, and I'm going to time it once again. This time we're going to be drawing about 30 amps on average from it, because as this voltage falls, this amperage will rise. So I'll just estimate about 30 amps on average. And we'll see how long this will run. Now this little segment here may seem a little repetitive, but it serves an important purpose. I just want to demonstrate that when you have a battery and you fully discharge it to 10.5 volts, that does not mean that your battery is fully discharged. There are curves, so-called Pukert curves, Pukert equation and such that you can find on the internet, but they're not adequately explained, and I'll explain some of the technicals of that later. But this is just a practical demonstration to show you that those numbers are bunk. They don't really mean much of anything in a practical circumstance. They're theoretical numbers based on empirical data that a scientist, a very intelligent scientist, did over 100 years ago, but the practical applications are just not there in most cases. So we had this battery, we drained it down to fully discharged, and at that point, the battery's fully discharged, right? You're done. Well, this is a demonstration to show you that, no, you're not done. That capacity didn't just disappear, it's still there. You just can't use it at that high of a load. So we reduced the load, and we got another 17 amp hours, which is pretty significant. That's almost half again as much as we pulled to start with. And now I'm using an even lighter load. This is a 30 amp load instead of an 85 amp load. And you can see that it's been running for 2 minutes, and we're still at 11.5 volts, which is great. 11.5 volts, it's not fully discharged at all, right? Even though we already did fully discharge it. So I'm going to let this run for however long it runs, and once again discharge this battery down to 10.5-ish volts. This inverter seems to be shutting off at about 10.7, but that's just fine. It'll save my battery from getting too sulfated, too damaged from these deep discharges. But I'll let this run for a while longer, and once again calculate how many additional amp hours we were able to pull out of this battery. We're getting toward the end of this 30 amp draw. The battery's now at 10.83 volts, and it has been running for about 37 minutes, which is pretty significant. I'll wait until this shuts down, and then we'll calculate how much more capacity we got from this battery. And the inverter has finally shut down at a little over 39 minutes. So let's jump back to my calculator. 39 minutes out of 1 hour. That's 0.65 hours. 0.65 hours at 30 amps is another 19.5 amp hours. So we already got 67 out of it, and if I add 19.5 to that, we're up at 86.5 amp hours. Now, we're starting to get close to this battery's rated capacity. So if we just keep lowering the load, we're going to get more and more capacity out of this battery. Now let's take a look at the battery ratings real quick. So this is what's actually printed on the battery. 12 volt battery, 100 amp hour capacity at the C/10 rate. And that means that 100 divided by 10, which is 10 amps. So the C over 10 rate is the 10 amp rate. I've discharged this battery at a 30 amp rate, which is 3 times what this battery is rated for. So it's no surprise I didn't get 100 amp hours out of it yet. And they say at 20 degrees Celsius, which is very close to the temperature that we're currently operating it at, and discharge down to 1.8 volts per cell. 1.8 volts per cell, there's 6 cells in it, so that means 10.8 volts, which is almost exactly what we're discharging it to. So if I ran this again at a 10 amp load, I could expect to recover the remaining 13.5 approximately amp hours out of this battery, which is very reasonable. And most likely I could do that, but I don't really want to spend another couple of hours sitting here watching this inverter, listening to it beep at me. So I'm going to stop it here. It's not good for the battery to drain it that low anyway, so I will terminate this test here and recharge the battery. But I think this is an adequate demonstration to show that you don't actually lose much at all of capacity in a battery by discharging it at a rapid rate. That's not what the Peuckerт equation means. I also want to mention that because these batteries are brand new and have only just received their commissioning charge, you only get, according to the data sheet, about 90% of the rating of these batteries. That's all that you're expected to get on the first discharge cycle. After a few dozen discharge cycles, you'll end up with the 100% of the capacity. And I should also mention one more thing about them, that this is an industrial battery. You cannot trust the ratings of a standard battery that you buy at an auto store or at Walmart, because the quality control on those is horrendous. They know that nobody ever checks those batteries, and you'll get huge variations from battery to battery. You cannot trust those ratings, and they are not a good battery to do a scientific type test like this on. This is a battery that is exclusively marketed toward industrial and commercial customers, and they do test every parameter of these batteries. The shelf life, the cycle life, the internal resistance at different temperatures, at different discharge rates, the Coulomb efficiency, the voltage efficiency, all kinds of things, including what I'm testing right here. And if these did not meet this specification, they would hear about it. So we can pretty much be guaranteed that this battery does meet these specifications, which is one thing that does make it a good test subject for this test. Now, just in the time that I've been blabbing away looking at the battery label, you can see that the voltage of the battery rose back up to 11.5 volts. So I could redo this test once again with a single 100 watt light bulb, for example, and see how many more amp hours I can pull from it, but I think it's pretty clear that we would eventually get to the label rating, 100 amp hours, with no problem, and even surpass it, I'm quite sure. So this has some obvious implications for paralleling batteries. And I guess it's obvious, but I'll explain it anyway. So with this particular battery here, we can power a 130 amp load. I'll just call it a 1500 watt electric heater, which is what I had. We can power a 1500 watt electric heater from it at a 50% state of charge. After that, you can no longer power that heater. But the battery's not dead. There's still capacity in it. If you discharge it to 70% discharged or 30% state of charge, you can power a 800 watt heater. And after that, you can't power that heater anymore, but you can still power other stuff. If we discharge it to down to 15% state of charge or 85% discharged, we can power about 300 watts out of it, 300 watts of light bulbs. And after that, there's still capacity left, you just can't pull it out at more than a 300 watt rate. So, if we take this battery and put 10 of them in parallel, for example, now you can power that 1500 watt electric heater until these batteries are down to maybe 10% state of charge. And that gives you a huge benefit in terms of their capacity. And I'm going to directly demonstrate this now by taking this battery and recharging it, because I don't want to store it discharged, that will ruin it, and take 2 more batteries, which I have on the floor down here, and hook those up to this inverter setup. And then I'm going to go back to that original configuration with the 1500 watt heater and see how long that I can power it. I was only able to power it for 23 minutes initially off of this battery, and let's see how long I can power that heater just by hooking up two identical batteries in parallel. Alright, this is the exact same setup. I have the same inverter, two new batteries that have not been cycled and have just received their commissioning charge that I showed at the beginning of this video. They're connected in parallel with 2-gauge cabling, and I'm using the same 2-gauge cabling from these batteries to run the inverter. They're starting at about the same voltage here, and I have the exact same electric heater set on high. Last time I did this, it lasted 23 minutes off of one battery, and my claim is that it will last far more than twice as long with two batteries. So let's test my claim. I'll go over here, turn the inverter on. That is on, the heater is on high, and I will reset my timer. And this is now running. And once the inverter shuts off at about 10.8 volts or so, it seems, we will see how long this heater has been running on high and see if it is greater or lesser than 2 times 23. And the inverter is just about to shut down, I believe. 10.7 volts on the meter, and there it goes. I will now turn the inverter off so it doesn't turn itself back on. And let's check the stopwatch. We are at 1 hour and 1 minute. 1 hour and 1 minute is what we got out of both of these batteries in parallel. Out of just one battery, we got 23 minutes. So, turn on my calculator. That is 61 minutes instead of 23, and it lasted about 2.7 times as long. So, two batteries was 2.7 times greater than one battery. 1 plus 1 equals 2.7. That's the result that I got with these specific batteries. And I do want to note once again, I said this at the beginning of the video, but these batteries, because of their high quality, are not the best batteries for this demonstration. If you used really cheap batteries, automotive batteries or something like that, you would get a much larger effect from paralleling than you do here. But even with these top quality batteries, you still get a significant benefit. So if we look at 61 minutes out of 60, and at 130 amps, that is 132 amp hours that we were able to get out of both of the batteries, versus just 50 amp hours out of one, and 200 amp hours total. So we were able to power this 1500 watt load from batteries that were 66% discharged in this case, because we had two in parallel. With just one, this heater would not run after they were about 50% discharged. So with this demonstration, I believe that I have shown two things. One, that 1 plus 1 does not equal 2 when it comes to batteries. Paralleling them gets a large benefit. And two, that the Puchert equation that many people are familiar with does not work like most people on the internet claim that it does. Those electrons don't disappear. You don't just lose the amps. It's simply a empirical model that someone came up with and not very practical. A 100 amp hour battery will have about 100 amp hours in it, and it matters very little what rate you discharge that battery at. You will still have 100 amp hours in it. It just may not be a useful capacity at a high discharge rate. And that is really what the Puchert equation is trying to say. So in the first part of this video, I have demonstrated with a practical demonstration with real batteries, a real inverter and a real load, that paralleling batteries gives you a large benefit. And in the second part of this video, I'm going to describe the technicals as to why that is the case. And there are not many good explanations out there on the internet why it works this way. And really, it's fairly straightforward. I'm going to cover just enough of the technical details to allow you to understand the concepts behind it. And I think once I cover this, for those who have at least a rudimentary understanding of electricity, it will become pretty clear how this process actually works. And I am not a chemist, so I'm not going to go into the chemistry of these batteries. That's very complex. It's very difficult to properly model a battery. There are many different models out there for different purposes. Nobody has a perfect one. I'm not going to cover that, but I'm at least going to describe why these batteries behave this way.